Let's just recap from class today the formal definition of what a derivative is. A derivative is really nothing more than the limit um, over a small interval in a function, defining the slope of that function between 2 points, the average slope, and it's the limit of that average slope as the interval, the x-axis interval approaches zero. So let's take a quick look here. I'm going to actually zoom way in on this function that I've drawn. And I'm not using distance and time here, I'm just using y and x. So let's say I zoom way, way in, and I make this nice little triangle showing my rise, which is my delta y, and my run delta x. You can see that this little triangle here is actually a pretty good approximation if we're thinking about approximations to the slope of that line. But let's label some points here. So this first point is just going to be x and y of x. That's just the regular point on the function where we are. And since we've moved over by delta x here, this is x plus delta x, and y of x plus delta x. So it's the function evaluated at the point x plus delta x. Whereas over here, if I want to be consistent, this is x and y of x. Okay, so the slope, like we talked about, equals rise, which is delta y, over run, which is delta x. And right now, this slope is really representing an average. If this were a position time graph, this slope would be representing the average velocity over that very small time interval. This is actually how a speedometer calculates your speed. It measures your average speed over a very tiny little time interval and says it's, kind of approximates it as your speed at that moment, but it's really not over a moment, it's over a period of time. And so we have our slope, which is delta y over delta x. And if I were to now zoom all the way back out, so let me do that, you can see what I've done. Let me just reset there. So I have really just this tiny little thing, you can't even read it anymore. It's this super tiny little slope calculation of the function. And so the formal definition of, if I were to actually write, let's do it this way, if I were to write the average slope, that's going to be just the straight delta y over delta x. And that's going to equal y at x plus delta x minus y at x, so the delta y term, y evaluated at those 2 points and subtracted, divided by delta x. That gives me my average slope. That average slope becomes an instantaneous slope or a derivative once we take the limit as delta x approaches zero. We squeeze that function down over a very small time interval. So the limit of delta y over delta x as delta x approaches zero is the derivative. That is the definition of the derivative. The notation for that, we move away from deltas and we go to d's. So dy over dx, and it's not really a ratio, it's more of a representation of the concept of this squeezed down limited rise over run. That is your derivative. It's also sometimes written as y prime of x. That's other notation that we'll see. It's also sometimes written as d by dx of y of x. Those are all ways to write the derivative. We'll kind of use both of these in physics. So dy dx is the limit as delta x approaches zero of y at x plus delta x minus y at x over delta x. That's the formal definition. Whenever you're trying to prove a relationship of, for derivatives or a rule for differentiation or any of that, you always go back to this formal definition. In the next example, I'm going to use that formal definition to calculate a few different derivatives for you. Once you learn the rules, you don't really go back to this formal definition unless you really want to prove something. But it's really good to develop your understanding by using it in a more sort of brute forcey kind of way because it really helps you see what you're actually calculating. When we learn about integrals, we'll come back to a similar definition, do the same thing. It's really helpful to go back to these basic fundamental definitions. Okay, more in the next video.